Okay, hi everyone, welcome back to this video series on data centers. Binary to decimal and hexadecimal conversion. Before we get into working with the TCP/IP protocol and IP addressing, it's really important for you to truly understand the differences between binary, decimal and hexadecimal numbers and how to convert one format into the other. So we'll start with binary numbering. It's pretty simple really. The digits used are limited to either a 1 or a 0, and each bit is called a bit short for a binary digit. Typically you count either 4 or 8 bits together, with these bits being referred to as a nibble and a byte respectively. What interests us in binary numbering is the value represented in a decimal format, the typical decimal format being the base -10 number scheme that we've all used since kindergarten. The binary numbers are placed in a value spot starting at the right and moving left, with each spot having double the value of the previous spot. Table 3.1 shows the decimal values of each bit location in a nibble and a byte. Remember, a nibble is 4 bits and a byte is 8 bits. Nibble values 8421, byte values 128, 64, 32, 16, 8, 4, 2 and 1. What all this means is that if digit 1 is placed in a value spot, then the nibble or byte takes on that decimal value and adds it to any other value spots that have a 1. And if a 0 is placed in a bit spot, you don't count that value. Let me clarify things. If we have 1 placed in each spot of our nibble, we would then add up 8 plus 4 plus 2 plus 1 to give us a maximum value of 15. Another example for our nibble values would be 1010. That means that the 8 minus bit and the 2 minus bit are turned on, which equals a decimal value of 10. If we have a nibble binary value of 0110, then our decimal value would be 6, because the 4 and the 2 bits are turned on, but the byte values can add up to a value that's significantly higher than 15. This is how, if we counted every bit as a 1, then the byte binary value would look like this. Remember, 8 bits equal a byte. 1111111. We would then count every bit spot because each bit is turned on. It would look like this, which demonstrates the maximum value of a byte. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255. There are plenty of other decimal values in a values that a binary number can equal. Let's work through a few examples. 100101110. Which bits are on? The 128, 16, 4 and 2 bits are on, so we'll just add them up. 128 plus 16 plus 4 plus 2 equals 150. 01101100. Which bytes are on? The 64, the 32, the 8 and the 4 bits are on. So we just need to add them up. 64 plus 32 plus 8 plus 4 equals 108. 11101000. Which bits are on? The 128, 64, 32 and 8 bits are on, so we just add up the values. 128 plus 64 plus 32 plus 8 equals 232. So here's a binary to decimal memorization chart. You can have a quick look at that there. I'm not going to read through all of it. Hexadecimal addressing is completely different than binary to decimal. It's converted by reading nibbles, not bytes. By using a nibble, we can convert these bytes to hex pretty simple. First, understand that the hexadecimal addressing scheme uses only the numbers 0 through 9, and since the numbers 10, 11, 12 and so on can't be used because they are 2-digit numbers, the letters A, B, C, D and E and F are used to represent 10, 11, 12, 13, 14 and 15 respectively. And here's a hex to decimal binary chart. I'll just leave it on the screen there if you want to have a quick look at it. Okay. Did you notice that the first 10 hexadecimal digits 09 are the same value as the decimal values? If not, look again. This handy fact makes those values super easy to convert. So suppose you have something like this 0x6a. Sometimes Cisco likes to put 0x in front of characters so you know that they are a hex value. If this doesn't have any other special meaning, what are the binary and decimal values? All you have to remember is that each hex character is one nibble and 2 hex characters together make a byte. To figure out the binary value, we need to put the hex characters into 2 nibbles and then put them together into a byte. 6 equals 0, 1, 1, 0 and A, which is 10 in hex equals 1010. So the complete byte would be 011011010, which is 106 in decimal. To convert a longer hexadecimal number such as 0x718, you do the same, but the binary would be longer. 111 0 0 0 1 1 0 0 0, and you just keep counting from left to right. Let's give it a shot, but first let's look at our possible numbers. Starting on the right, just keep doubling the numbers and don't stop at 8 bits, but this time the valid numbers are 8, 16, 256, 512 and 1024, which equals 1816 in decimal. Let's do this one more time. 0xc84 in binary, it would be 110010000100. The valid numbers are 4, 128, 1024, 2048, which equals 3204. Now to convert from binary to hex, just take the byte and break it into nibbles. Here what I mean, say you have the binary number 01010101. First break it into nibbles 0101 and 0101, with the value of each nibble being 5, since the 1 and 4 bits are on. This makes the hex answer x55 and in decimal format, and the binary number is 01010101, which converts to 64 plus 16, 4 plus 1 equals 85. Here's another binary number 11001100. Your answer will be 1100 equals 12 and 1100 equals 12, therefore is converted to CC in hex. The decimal conversion answer will be 128 plus 64 plus 8 plus 4 equals 204. One more example that we need to get working on the physical here. Suppose you had the following binary number 10110101. The hex answer would be 0xb5, since 1011 converts to B and 0101 converts to 5 in hex value. The decimal equivalent is 128 plus 32 plus 16 plus 4 plus 1 equals 181. Ethernet frames. The data link layer is responsible for combining bits into bytes and bytes into frames. Frames are used at the data link layer to encapsulate packets handed down from the network layer for transaction on a type of media access. There are three types of media access methods: contention, Ethernet token ring, token passing, and FFDI and polling, IBM mainframes, and 100VG ANILAN. Although token passing and polling are not typically used in today's networks and are in the objectives just for SCT, the function of Ethernet stations is to pass data frames between each other using a group of bits known as a MAC frame format. This provides error detection from cyclical redundancy checks, CRC, but remember, this is error detection, not error correction. The 802.3 frames and Ethernet frames are shown in figure 3.3. Following are the details of the different fields in the 802.3 Ethernet frame types. Preamble. An alternating 1-0 pattern provides a 5 MHz clock at the start of each packet, which allows the receiving devices to lock the incoming bit stream. A start frame delimiter, SFD sync. The preamble is 7 octets and the SFD is 1 octet sync. The SFD is 10101011, where the last pair of ones allows the receiver to come into the alternating 1-0 pattern somewhere in the middle and still sync up and detect the beginning of the data. Figure 3.3. 802.3 in Ethernet frames formats: preamble 8 bytes, DA 6 bytes, SA 6 bytes, type 2 bytes, data FCS 4 bytes, preamble 8 bytes, DA 6 bytes, SA 6 bytes, length 2 bytes, data FCS. Destination address. This transmits a 48-bit value using the least significant bit, LSB, first. The DA is used by receiving stations to determine whether an incoming packet is addressed to a particular node. The destination address can be an individual address or a broadcast or multicast MAC address. Remember that a broadcast is all ones or Fs in hex and is sent to all devices, but a multicast is sent only to a similar subset of nodes on a network. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.